welcome back to our web series on how to utilize Mplus to estimate our first structural equation model. My name is Lewin van Sail and I will be taking you through the next section. So in this, let's get a little bit of a recap from our previous video. So in the previous video, we briefly spoke about the Mplus environment, the syntax, how to estimate by statements, with statements, and on statements, so factor loadings, correlations / covariances, and regressions. And now we look at the data that we'll be utilizing for the remainder of this web lecture series. Today, we'll be speaking specifically about measurement models, and that's the very first big step in your journey to becoming Mplus masters. So as I mentioned in our previous lecture, that you can estimate measurement models in various ways. There are various strategies, but we will be utilizing what we call a confirmatory factor analytic approach. So what this basically means is we construct different factorial models of each of our instruments and compare whether or not these different permutations fit our data the best. Now, the function of the measurement model process is to systematically compare competing theoretical models with one another to figure out which model fits our data the best. Okay? And there's a certain process that we follow in order to do this. But don't worry, I will take you through every single step. So, remember, this is our theoretical model. We wanted to test whether person-environment fit predicts happiness and happiness predicts task performance. So in effect, we want to determine the relationships between these factors. That is our first objective. And to answer that question, we have two steps. We have measurement models and we have structural models. So for the measurement model component, we are going to estimate various versions of this model in Mplus and see whether or not we can actually get one to fit. So we're taking the first model that we'll be testing is we're taking our remember the comparative fit model indices. So these are the things that we're going to be utilizing to see whether or not our models actually, one, fit our data, and two, how does it compare between other models, right? So we'll be utilizing the fit indices and we'll be looking at measurement quality. Measurement quality refers to item fit, it refers to significant loadings, it refers to significant variance being declared, no negative residuals, but I'll take you through this in each single step. But it's important to remember these indices. So focus on this because we'll be utilizing this as an indicator for fit. So our TLI and CFI needs to be 0.9. That's usually the first thing that we look at. So we'll be translating now our theoretical model into our measurement model. So this is the first model that we're going to be testing because theory tells us that this should theoretically be the best fitting model for the data. All right. So we'll be testing person environment fit as a second order factor made up of three first order factors, happiness as a second order factor made up of two first order factors, and task performance as a one factor model. And because this is a measurement model, all of the interactions are correlations. So all factors are covaried between each other. Remember, dual arrow, covariance / correlation, depending on what we want to do. So let's go over to Mplus. So I have already put together the data set. As you can remember, the title, we specified our data. It's in, as you can see, it's in the same folder as what we have. So our data is in the same folder. Here is the list of all of our variables. We specified missing values as -999. The variables that we'll be utilizing for this analysis is the one, all the items measuring task performance, all the items measuring meaning and engagement, and all the items measuring person environment fit. Important to remember, as I said in the previous lecture, when you estimate your measurement models, your competing CFA approach, you always estimate the entire model, not just one specific factor at a time, and then at the end putting them together. You always specify everything together. Why? Because we lose variance if we estimate a model and then we add it into a different model. That's one reason we get worse fit for that matter. So there are lots of reasons that we have to utilize this, but the most important is that in some cases certain latent variables borrows degrees of freedom from other models in order to help it to estimate properly. So always remember, it's very important. Our analysis part, as I said, we're utilizing the maximum likelihood estimator, and now we get to the core of our model. So the first thing is we have 3 first order latent factors, right? Oopsie. Oh, oopsie. Let's see if I can bring this back. We have these 3 factors that we want to test. So person, environment, person organization fit, need supply fit, demand ability fit. So I specified them, person organization fit, by the items that is in the questionnaire that tells us that these 3 items measure person organization fit. So person organization fit by item 4, 1, 4, and 7. Need supply fit by item 2, 5, and 8. Demand ability fit by these 3 items. Now, the only thing that is a little bit complicated now is for us to create this factor, the person environment fit factor. How do we do that? We say fit, you can call it whatever you want, by this factor, and this factor. Right? Pretty straightforward. We do the same thing with engagement, where we add engagement with all of its items, meaning all of its items. Oh, that's not supposed to be in there. I have to use that later. And happiness by engagement and meaning. And task performance is made up of these 6 factors. The outputs that we are requesting, we want sample statistics. Why? Because we want to check the distribution of the data. You remember, the distribution of the data indicates the type of estimator that we use. So we look at skewness and kurtosis as an indicator of multivariate normality. Modification indices, this will help us to see how we can improve our model. If we can correlate certain things with one another, will it enhance our model fit? Will it decrease our chi-square? So what this statement says, mod indices 40, and all that I'm saying here with the 40 is that I just want it to output relationships and things, modifications that we can make that will decrease the chi-square with a minimum of 40. This is something for later, and we want to standardize results so we can compare. So let's run the model and see. So you click on run. Always have to save, otherwise it doesn't work. And here we go. So my interface looks a little bit different than yours because I'm utilizing the HTML output just to make it easier for me to click on things. So don't worry too much about that. First that you see is the instructions, what we've indicated. Here is just an overall analysis of what we have. Here are the number of people in our sample, so 311 people. There's only one group that we estimated. There are 27 dependent variables, so there are 27 factors, observed things, and 8 of them are continuous, specified. This is just the covariance, not really interested in that at the moment. Here is our first part of our sample statistics. It is the specific means, the actual means of each one of the items, not the factors, the items. Covariance is not so important, but this is what we're interested in. So here you'll see that our sample size kind of differs a little bit, right? So all that Mplus does is that it skips over the numbers that are missing, that are missing on this specific item to help us to estimate better. Here is the actual means and variances, but we are interested in looking at the skewness and kurtosis. So anything bigger than 2 and bigger than plus 2 and smaller than minus 2 indicates non-normality in small samples. So let's quickly check. Are they all smaller than 1 or smaller than 2? Yes, smaller than 2, smaller than 2, smaller than 2, smaller than 2. Yes, everything is normal, so we can continue with the ML estimator. So the first thing that's important for us to notice is the model fit statistics. Now, who can remember what the criteria was? Let's first look at CFI and TLI. Are they bigger than 0.9? Yes, they are. So we can move on. Good model. Is our RMCA smaller than 0.8? Yes, it is. Does the confidence interval include 0? No, it doesn't. So is the probability non-significant? Yes, it is. Great. Is our SRMR smaller than 0.8? Of course it is. Perfect model. But here's a little problem. Chi-square is an indicator of model misfit, right? So we want actually a 0 value in the perfect world, which we'll never get. But that's what we want. So the closer to 0, the better the model, but we want it to be non-significant. Now, unfortunately, it's significant in this case, but we also know that chi-square is sensitive to sample size and it is sensitive to model complexity. So we've got a very simple model and we've got a very small sample size, so it's non-significant, so it's not that big of a problem. You have to report it though, but we have a whole bunch of other metrics in place that help us to justify that this model is a good fit. You will notice I didn't speak about AIC and BIC values here because we only utilize this to compare models with one another. So when we have the next model, we will look at the differences between this and the other one. So the lower one of the two will have a better indicator. We go to the standardized model results next, and this is where you look for measurement quality. So every item loading here needs to be bigger than 0.4, right? And it needs to be significantly loaded. So everything loads significantly. Great. All the values with the exclusion of 6 and 17 loads high. So if our model didn't fit, we could take these items out and it would improve our fit quite dramatically. These are the specific loadings from the second order factors onto the first order factor to the second order factor. Same here. You will see Mplus automatically, we didn't specify a with statement, right? It automatically specifies the relationships between all of the factors. And they're all significant. Just notice this one though. For now, it's significant, right? In our third lecture, this is going to become important. So quite high correlations, which is quite nice. Variances, everything fine, nothing non-significant, almost, but not. These are the specific variances that each of the specific items declare, but we are more interested in this. So these are the specific variances that's declared by each of the factors. So the items on engagement, the items on meaning declares that amount of variance, and so on. Okay. Modification indices, this comes out to help us to improve our model. Now, it's really important to remember we really actually don't want to modify items. We don't want to correlate error terms. Why? Because it brings up other challenges. When we parcel items, for example, we're changing the theoretical model that we're technically testing. But for argument's sake, I'm going to show you one thing. So if we correlate 12 and 2 on the authentic happiness scale, it will decrease our chi-square by 64. Another important point is whenever you actually do correlate error terms, there needs to be a theoretical justification for it. And that, for example, means you can only correlate items from the same subscale. For example, you can't correlate something from person environment fit with happiness, for example. It will not be appropriate and it would not be theoretically driven. So I want to do two things quickly. I want to go back to our model output and I want to copy this just to show you. So I'm copying model fit I've already done it here. And I am going to run the model again, but I'm going to add this. And what I'm doing here is we are not correlating the actual items, we are correlating the error terms on the items. Okay? So we're basically saying these two things measure the same thing, but we have to check this first. So meaning OS 2, yes, and 12. So they are measuring the same construct, so we can correlate them. You can't correlate item 1 here with item 17, for example, if the output told you to do that. Okay, so let's run it and see what happens. So here is our model fit, and let's compare it to our other one. So now we utilize AIC and BIC values. So our original model had a AIC of 22037. Here it is 21982. So which one is better? Original model or modified model? Which one is smaller? AIC. Great. Same with BIC. 2230, 22370, 22319. Smaller, therefore this model is better. Chi-square, unfortunately still non-significant, but chi-square is now 523, where originally it was 580. So it decreased by 60%, but we sacrificed 1 degree of freedom. So we took 1 degree of freedom away. You'll also see that our RMC is a lot better versus the original model. Our TLC and TLI and CFI is a lot better by like 0.02, where it's like 9.4 here, 9.2 there, 9.3 and 9.1. So this is a lot better model than this one. But like I said, we do not really want to modify models unless it is really necessary. So unless the model did not fit at all, then we can do some modifications. And an important point, there will be, if I show you, let's just do this like 3.4. If I ask for anything that will decrease chi-square by 3.4 or more, there will be a lot of factors that can increase chi-square. We always start with the biggest one first. So if we had to do this again, I would correlate, the next step would be TP1 with TP2, right? Because it measures task performance. That would decrease it by another 40%, another 40 base points. But we don't correlate everything at once. So we don't take this one and then this one and this one all together and specify it. We do it incrementally. We first do the biggest one, then we run it again. Then we look at what the next biggest one is and then do that one. Because the biggest one here, after this one, might not be the biggest one when you run it again if you've done the modification. Okay, so this model fits the data quite well. Perfect. Let's go on to our next model then. Sorry for that. All right, so you've tested this one and it works. Now we are testing the next theoretical model. So theory also tells us that all of the items, so all of the items that we had on these factors could load on that. So we could have a one factor model for person environment fit. And then we test this again, right? So let's go back to Mplus and see what happens. So one factor model for person environment fit. So in the previous model, you saw that there was like the demand ability fit and need supply fit. So nothing's changed here. All that I've done now is I've created a one factor model from fit by putting all of the items to load directly on fit with the by statement. Everything else stays the same. So let's run it and see what happens. Let's go to our model fit statistics. Let's take our best fitting model. Wait, let's first do this. Let's first look at the criteria. Does it fit the model? Is that bigger than 0.9? No. 0.9? No. So automatically we can already reject this just based on these two factors. This one, if you round it off, it becomes 0.8 and it hits that border. So all in all, this model we will automatically reject. And if we have to compare it to our other model, our best fitting model, we will see that AIC here is 22330. Here it's 22033. So it's a lot lower. 22652, 22370. This one is a lot lower. Chi-square 879580. This one is better. RMC is 0.8 basically, 0.5. TLI 98. And this one is a lot lower. So do you see? Our original model seems to fit the data better than this one. Okay. That's all that we're interested in at the measurement model part. Next model. Our third model will be, we keep person environment fit as a one-factor model, but now we say happiness is also a one-factor model. So all of the items from engagement and meaning can load directly onto happiness, and this one stays the same. Okay, so this is another theoretical model that we test. And remember, we're testing these things to figure out which model fits the data best. So let's go here. Nothing has changed. The only thing that I've added now was to say that happiness is made up of all of those items on meaning and engagement directly onto it. Pretty straightforward. We click run. We go to our model fit information. You can see it doesn't fit. If you round it off, it becomes 0.8. So automatically it doesn't fit. So we can reject it just based on that criteria alone, where all of our original model is still better. Better TLI, CFI, better chi-square, 900 versus 500, and so on. So model 1 is still our best model. Okay. Next. The next model we want to test now is to say, we want to see if this is a 3 first order factor model with the second order factor. If we just change happiness to a 1 factor, this to a 1 factor, what will work? Okay, so this is our fourth and possibly final measurement model. Okay, and you already know what we're going to do. So everything in our measurement model stays the same. I'm just estimating these factors again: person organization fit, need supply fit, demandability fit, and overall person environment fit. Remember, items directly onto it. So theoretically, the questionnaire said these items load onto that factor. So we have person organization fit by item 1, 4, and 7. The same with fit. We create a second order latent factor. So we create, let me just get this here. We create this factor by saying this factor is made up of this latent factor, that latent factor, and this latent factor, and everything else stays the same. So let's run. Okay. Oops. So let's look at it. TLI CFI, it's so close. If you round it off, it becomes 0.9 and 0.91. So this is in place, this is significant, this is small. Yeah, so what do we do now? We've got two models that kind of fits, right? So it meets the criteria. And this is going to be your job in the next slide to figure this out. Okay. Interesting enough, we can also enhance the model fit of this model by first, again, see 2 and 12, correlating them. But let's also quickly look why 2 and 12 is an issue. So we look at our standardized results. Item 2 seems to load quite okay, I guess. Item 12, okay. Seems fine. Seems fine. Interesting. 6 has a non-significant loading. Not too important though because it compensates, but just interesting to note. Variance is again declares quite a lot of variance, not bigger than 0.9 and quite small, so that's kind of nice and significant. Okay, that's the third model that we've tested. So remember this criteria. So these are our 4 models. I am now going to ask you to pause the video, right? And you go through them and see which models fit the data and fit the criteria, right? And I'll explain it in a minute. So pause the video here and try and physically you compare the specific differences between these models, because you have to report that in your paper. Okay, welcome back. So let's see. Before I show the answer, I just quickly want to show you also that each model has different numbers of parameters that are estimated. So this one has the most, it's the most complex, and this one is the least complex. This one was our theoretical model. This one was the one with all of the factors, just one factor models. So every time that you add something to your model, it takes away, or it adds one of these little things. Okay. So, yay! Our best fitting model in effect is model 1. But again, like I said, that is still an issue, so you always have to report that. But now, what do we do with this model? Because it does meet the criteria, right? If you run it off and you can modify it, but so what do we do? 2 things that you could do. You could also specify it. If this model, for example, was your theoretical model, you could have indicated that this model fitted it better, so you would have rejected that. Or if it's an important model for your case, you could also transfer it to your structural model and then do an assessment for both this one and this one. I've seen that a couple of times, not a lot, but there needs to be a theoretical argument for it. But I would reject this model based on the fact that it does not meet all of the criteria, right? And that this model fits the data a lot better. Remember, AIC values, smaller, here, BIC, bigger, chi-square, bigger, degrees of freedom, more, lower, bigger, bigger, almost significant actually. So you see this model, even though if you compare it, you can see that this model's AIC and BIC values are lower than, or the AIC value is lower than this one, and the BIC value is bigger than this one. So apples and pears, right? But you have to make that decision. You can actually also argue that RMISA is, if you set very strict guidelines for 0.01 significance level, then this one does not meet the criteria. Then you can also reject it based on that. But it's important to specify all of the criteria in your method section. So overall, model 1 seems to fit the data best. Okay, activity 2. I want you to now go and take the syntaxes that's there, and I want you to run this measurement model, where person environment fit is a 1-factor model. We do not have a second order factor for happiness, so we have engagement and meaning as independent factors, and we have task performance. So I want you to go and create the syntax for me and run it. And then I want you to compare it to the other models and tell me which one is the best. The memo will be available in the comments. Okay. As always, if you have any questions, you know where to get me. And thank you for listening. Have a great day.